overall quality of normal research paper is way lower than MRAS. MRAS now is more than what it yeah, so that's why definitely a very good way. It's much harder to put wafer and stay away for those European waters. That they can get it.
Okay, welcome everyone after a long winter break. We did have some winter days, and we're all back. Classes started, and everything looks good so far. And we are very delighted to have our first speaker being Catherine Zucker, who is in the ITC, and we're very pleased to have her with us. And she will tell us about the formation of the local Fluff, which sounds exciting, actually. And then we'll hear from Kristina Monsch, also from the CFL. Where is Kristina? Oh, there she is. And she will talk about high-resolution SMA and Pan-STARRS observations of Draculas Chivito. Okay, you will explain what that is. It sounds very frightening, actually. The largest protoplanetary disk in the sky. And then we'll hear from another relatively local person from MIT, Minghao Yue. He's over there. And he will talk about detecting the host galaxies of high-redshift quasars. And finally, Wang from Peking University, sitting over there at the end. He will tell us about connecting galaxies across cosmic times. And once again, I just wanted to thank Eric Quito for donating the funds that allow us to meet on a weekly basis here. Thank you, Eric.
Can you guys hear me?
Do you have a microphone on?
I do have it on. Oh, now can you hear me? Okay, perfect. Okay, thank you, Avi, for the introduction. As Avi said, my name is Catherine Zucker. I rejoined the CFA last summer as a Smithsonian astrophysicist, but I was previously a Harvard grad student here, and I'm very, very happy to be back permanently. And today, I'm very excited to talk to you about the formation of the local fluff. And I'll explain what the local fluff is in a second. But before I begin, I just want to thank my wonderful collaborators on this research, Seth Redfield, Sarah Starczewski, and Ralph Koniecka, who's a PhD student here at Harvard. So in order to explain what the local fluff is, I need to provide a context on another structure called the local bubble, which some of you may have heard of. So we live inside a cavity in interstellar space called the local bubble. So we've known about this local bubble for about 50 years. This is an artist's conception of the local bubble. We lie very close to the center. So we know we've lied in a region that's lower density, higher temperature, and more highly ionized than the surrounding medium. But what we just learned about recently in the last 2 to 3 years is that there's actually a buildup of dense star-forming gas on the surface of this local bubble that you can see here in purple. And so we think that this arrangement of dense gas near the sun and the fact that we live in this interstellar cavity is the direct result of supernova explosions that occurred near the sun in the past 14 million years or so. And so we think about 14 million years ago, these powerful supernovas started exploding, about 15 over the last 14 million years, and these powerful supernova carved out this bubble of hot gas and swept up the surrounding medium and led to this pileup of dense gas and young star formation on the surface you can see here again in purple. And so what I want to talk about today is not actually what's going on the surface of the bubble, but actually what's going on inside this bubble. So just to emphasize why this is cool, so the sun has actually been traveling within the confines of the local bubble for the past 6 million years or so. So you can see this is the sun's trajectory, and you can see this is the expansion of the bubble. So we crossed through the dense shell of the local bubble about 6 million years ago, and so we've been traveling interior to it within the last 6 million years. And so the focus of this talk is understanding what's going on in the interstellar environment inside the bubble in which the sun has been traveling. So there's a common misconception that this local bubble is totally empty, and that's not the case. There is structure inside the local bubble, and the most famous of this structure is something called the local fluff, which is the subject of this talk. So what we're going to do is we're going to zoom in to the nearest 10 or 15 parsecs of the sun. And we're going to make a zoom out view. And this is an artist's conception of the local fluff. So the local fluff is sort of this blue stuff. It's sort of warm neutral, warm ionized gas. It's the interstellar environment that the sun is traveling through at this very moment. You can see Alpha Centauri here, a little over a parsec away. And so I would argue that if you took this fluff and you put it a kiloparsec away in the galaxy, no one would ever study this complex. It would not be the focus of any studies. But the fact that this fluff is our fluff, it is the fluff we are traveling through. It is the only interstellar environment in the entire universe that we can probe directly, immediately skyrockets it into incredible relevance. So just to drive this point home, this local fluff is the stuff that impinges upon our heliosphere. This is a model of the heliosphere provided by NASA, and you can see that Voyager 1 and Voyager 2 have actually left the heliosphere. They've passed the boundary of the heliopause, and they're traveling through interstellar space. And the interstellar space they are traveling through is the local fluff. And so it's critically important, because this is our fluff, that we understand not just the properties of the fluff, but exactly how it forms. And so that's the focus of this 10-minute ITC talk. So just to give you a very, very high-level overview of the properties of the fluff, so UV absorption line measurements, primarily from HST, tell us that the local fluff consists of roughly 15 distinct nearby, so about 10 to 15 parsecs of the sun, cloudlets that are pretty diffuse, so about 0.1 to 0.2 particles per cubic centimeter. So that's about 10 times denser than the average density of the rest of the interior of the bubble, but orders of magnitude less dense than the star-forming gas on the surface. It exhibits a wide range of temperatures, but it's typically about 5 to 10,000 Kelvin. It's partially ionized. But critically for this story, if you look at the 3D space motions of the local fluff, which you actually know because this fluff is so close to our noses and it spans such a large area of the sky, that if you assume that each individual cloudlet is moving as a solid body or rigid body, you can actually decompose how it's moving in 3D space of the galaxy. And we find, and previous studies have found, most notably Redfield and Linsky 2008, that all of these clouds are moving in roughly the same direction. And so I've overlaid here the vectors of the individual clouds in the local fluff. And so that's sort of the mean motion of the local fluff. You can see that if you actually overlay the trajectory of the sun, we're actually moving transverse to each other. So we're sort of like ships in the night, just sort of glancing by each other. And so the question is, how did this fluff form? And so there's a rich history in the literature. Most notably, John Slavin here at the CFA has done a huge amount of work in this topic. And so I'm going to propose a theory that we've come up with in the last year or two on the origin of the fluff. So the hypothesis that we're going to put forth is that the most recent supernova that exploded within the local bubble is directly responsible for creating the local fluff. What's really exciting is that the remnant of this stellar remnant of this supernova explosion is indeed known. And there's a study by Neuhauser et al. 2020 that actually took the progenitor clusters that we know hosted the supernova that powered the expansion of the bubble over the past 14 million years. And they traced that cluster back alongside nearby runaway stars and nearby pulsars in the solar neighborhood. And this study found that all three of these things, so the cluster that probably the supernova went off in, the runaway star, and the pulsar, that there's a remnant of this core collapse supernova, they met at the same location within the last 1 to 2 million years. So this supernova is the most recent supernova that has gone off in the last few million years within roughly 100 parsecs of the sun. And so we know that this indeed happened, and there was a recent nearby supernova explosion. And so what does this have to do with the fluff? So let's look at this 3D view, which I think is much more informative. This is a top-down view of the local bubble. You can see here that boundary of the bubble in purple. This UCL cluster, that is the local bubble progenitor cluster. That's the cluster that this runaway star and this pulsar were released in. And in the present day, it lies very close to the edge of the local bubble. And so if you assume, and obviously in the past it lied closer to the center because it carved out the bubble, but at the moment it lies close to the edge. And so if you assume that this supernova went off, which we have very strong evidence that it did, and we assume that it created this spherical shell expansion, that's sort of roughly what that spherical supernova remnant would look like. But critically, I want to overlay the motion of the local fluff. And so if you essentially compare the 3D space motion, the bulk 3D space motion of the local fluff, with the motion you would expect it to have if it was pushed or swept up by the supernova remnants, it agrees to within like 2 degrees. So it's exactly radial to this remnants. And so the hypothesis is that the local fluff's 3D motion is perpendicular to the surface of this remnants, and it's exactly the motion you would expect it to have if it was swept up by this remnant over time. And so the idea here is that we can model the evolution of this remnant given the fluff's 3D spatial and dynamical properties. And so I'm going to skip over all of the modeling about how we actually fit the expansion of this remnant to explain the fluff's 3D spatial and dynamical properties, but I'm going to get right to the punchline. So the local bubble here is in purple. You can see the solar orbit here in yellow. The UCL cluster orbit, that's the orbit that the supernova went off in. The cluster that the supernova went off in is here in green. And so we're going to go back from 1.5 million years ago to the present day, and we're going to see the supernova go off 1.2 million years ago. And we find that the best density that it goes off in is roughly 0.04 particles per cubic centimeter, which is about 2 times the average density of the bubble in the present day. So we're going to play this video, and you'll see the sun moves forward, this orbit moves forward of the cluster, and then you start expanding into this pre-evacuated cavity of the local bubble. You see these little red dots. Those are essentially predictions for when individual clouds in the local fluff condense in this expanding shell via various fluid instabilities and were swept up. And that's how you get this sort of transverse motion between the sun and the expansion of these fluffy little clouds. So what's really exciting is that our model actually provides a constraint on the age of these little fluffies. So it implies that these fluffy clouds form progressively over the past 1 million years or so. So we argue that the supernova went off about 1.2 million years ago based on our spatial dynamical modeling, and then shell formation occurs about 1 million years ago. And then you can see right after that, all of these clouds, they all have names, the clouds in the fluff, they start to form progressively. And so this blue line is the model for the evolution of this, velocity evolution of this remnants. And then these are the velocities of the various clouds in the fluff. And so they're all very young. They're all less than 1 million years old. They have a pretty large spread in ages. But ultimately, we do not think these fluff clouds will last very long in the harsh environments of the bubble. So it's a very transient phenomenon. They're very diffuse. But it's exciting because they're very close to home. And so just to conclude, we find that the local fluff is a product of the most recent supernova that went off inside of the local bubble. The remnant of the supernova explosion is known, and we think that remnant, based on existing studies from Neuhauser et al. 2020, went off about 1 to 2 million years ago, right close to the edge of the local bubble, just interior to it. As I said, the supernova occurred in the pre-evacuated bubble cavity, and so it swept up tenuous material and formed the local fluff and explains its 3D spatial and dynamical properties. And finally, the local fluff is young. We think that these fluff clouds formed progressively over the past 1 million years, and they're unlikely to survive long inside the harsh conditions of the bubble. But when we send potential future probes, like the interstellar probe, which is a proposed probe concept by NASA into interstellar space, if that's approved, it'll directly probe the properties of this local fluff. Thank you.
This all makes sense because 100 parsec is about 1% of our distance from the center of the Milky Way. So that means that if there is a supernova every 50 to 100 years, then we will have one supernova every million years within 100 parsecs.
Yep.
Because the area is 10 to the 4 times.
Yep, and that's exactly what we think happened.
Exactly.
Yeah.
So that means also that every million years there is a new one.
Yes,
So
yes.
why was the most recent one the most important one? Because there was another one 2 million years ago, and it could have shaped the environment similarly.
Yeah, so I think, I wouldn't say it's the most important, I would say it's the easiest to model. It's the only one that we actually have a direct remnant of. So in theory, if we knew the remnant of the previous one and we knew exactly how they interacted, I think that would be super worthy of modeling. It's just incredibly hard to model. Like, you have to assume that the ambient density is incredibly uniform, or you're just using very simple analytic sort of spherical shell expansion models for the evolution of these different phases. So I wouldn't rule that out as likely a possibility. There's cumulative effects. But in terms of this simple modeling, like, all the math works out. It can explain the motion, the positions. It can explain the column density, the temperature distribution. It can explain the orientation of the local magnetic field. So it all works out. It's almost certainly always more complicated, but this simple model is the first, I think, to self-consistently explain the timescales and everything like that.
Okay, so one supernova since humans existed on Earth, so.
Well, it depends on there's the Vela supernova remnant, but that's like 400 parsecs away. That's like 15,000 years old. But so it depends on like how far away you're looking. But this is my favorite one. I don't know if that counts.
Okay, there are lots of questions, so let's start here and then go.
Thank you. So this is very exciting for those of us who think about modeling out the impact of the ISM,
Yeah.
in this case Fluff, from, say, far UV and
Yeah.
EUV observation.
Yeah.
So do you think these kinds of maps are going to improve our modeling, or are they the noise of our efforts?
I think they will. The problem is, like, as you know, for a lot of this UV spectroscopy, there's like a lot of small. I don't know exactly what angle your question is coming from, but the challenge is that a lot of this modeling, I actually have a picture. Let's see. There's pretty small number statistics, so all of the properties of the fluff are based on probably like a few hundred measurements of UV absorption line spectroscopy towards nearby stars. And so there's small number statistics. There are efforts. Seth Redfield recently submitted an HST proposal to try to expand that. But in general, like, these measurements are very expensive. And so you want to build more complete spatial dynamical models, but you just need more background stars. So I think it's a work in progress. But I'm not sure if I totally answered your question.
No, you did, because we want to model the impact of the attenuation.
Yeah.
Right? And so this really.
Yeah, so the more background stars. So if anyone is reviewing an HST proposal of Seth Redfield, I would, and you find this interesting, I'm just putting that out there.
Okay, more questions. We had a lot. Go ahead.
I just want to get clear on the
Yeah.
picture that you're putting forward.
Yeah.
So the idea is that so it's a shock that's coming into an already existing cavity that's
Yes.
so it pushes the shell into the interior. Is that right?
Yeah, so it's sweeping up very tenuous material inside that's the model at least. It's pushing up very tenuous material inside the cavity. We're arguing this is in the pressure-driven snowplow phase, and you can get some sort of fluid instabilities, things like the Vishniac instability is possible. The model isn't exactly constraining the exact physical mechanism at which these condensations form in the shell, but we are assuming it's sweeping up very tenuous gas. I don't think we can entirely rule out that there's some existing, like, you have a paper in 2009 that presents that there's potentially like pre-existing overdensities in the bubble that could be shocked and swept up. So it could be either of those scenarios, but I've been meaning to talk to you for months, and so please, can we set up a meeting, because I'm really excited to talk about this.
Okay, more questions. Go ahead, Eric.
I was wondering why the motion of the sun is going through the local bubble.
Yeah.
I'm assuming everything is in circular orbit around here,
Yeah.
right? They're all moving together.
Yeah, so it's everything was put in respect to the local standard of rest. So basically what's happened, we're moving faster. At this point in time, we're moving faster than the bubble, the surface of the bubble is currently expanding. So with respect to the local standard of rest, the bubble expanded about 7 kilometers per second, so it's a pretty old remnant. We're moving through the ISM at like 26 kilometers per second, and so we were actually like lagging behind it in the galaxy when it exploded, and so we just happened to like be passing through. But this is just the frame of reference that we're adopting. Does that make sense? Okay.
This is very interesting work.
Yeah.
I'm aware of the Interstellar Probe mission, and
Yeah.
I'm curious, thinking of it creatively and speaking on the instrument side.
Yeah.
What might be of interest to probe even beyond current technology? Could we do a sample return mission? What else would you do?
Okay. You're asking the wrong girl here. I can tell you what sort of things, instruments are being proposed for the Interstellar Probe. So I'm not on this team. This is just my like passive observer who's very interested. There's like a suite of dust instruments. You can like probe the dust properties in these local fluffs. I think there's a magnetometer. Someone could probably tell me how to pronounce that. Magnetometer. There is a lot of stuff to do plasma physics. I don't know, John, I feel like you would know this. Do you have any other thoughts about the interstellar probe?
Yeah, so I mean, it's going to be able to see the interstellar dust from the local cloud, which is impinging on us.
Yeah.
It's going to be able to do, magnetic field, which is interesting, because that also affects the shape of the heliosphere.
Yeah. Yeah, it'll be really exciting. So yeah, hopefully they get to prove it. If it is approved, I think it'll launch in late 2036, late 2030s, early 2040s.
So that tells the audience which members will be alive.
Hopefully me. But also this is super relevant for like breakthrough starshot. Like if we try to get to Alpha Centauri, like the local fluff is going to be a problem. So it's very relevant.
Before we close this discussion, we have to move on. You were recently appointed as an important PI in the Roman, for the Roman. Can you tell us more?
Yes. So I'm very interested in probing the absolute nearest local fluff, interstellar medium, and the absolute farthest interstellar medium in the galaxy. And so I've been part of an initiative to try to survey the galactic plane with Robin. That would produce more stars in detections in the Milky Way than detected in any other survey. The combination of all surveys in the history of astrophysics combined, so it'll be like tens and tens of billions of stars. And for me, if you actually know properties of stars and you can detect them on the other side of the galaxy, which Roman will be able to do, you can actually use that to map the 3D distribution of dust in the Milky Way and uncover the interstellar environment of the Milky Way on the far side of the galactic center, which is like basically unknown. And so if you give us like 10 years, we'll map from the local fluff to like the far reaches of like the wild, wild west of the Milky Way. So it's very exciting.
Thank you so much for illuminating our neighborhood.
Thank you.
It's a million years.
Okay, awesome. Just fix the mic. Hi, everyone can hear me, right? So hi everyone, for those who don't know me, I'm Kristina. I'm a postdoc here in the High Energy Division. And I'll be talking about this disk called IRAS 23077 plus 6707, or with the much nicer name, Draculas Chivito. Draculas Chivito, sorry, before I go ahead, maybe I should have said this before, sorry. I also want to thank, obviously, my collaborators. Sorry, that was a bit of a mess now. I want to thank my collaborators, but most importantly, Josh Lovell, who's also a postdoc here at the CFA and who's been helping me a great amount with obtaining these data and also analyzing these data. So yeah, Draculas Chivito is an edge-on protoplanetary disk that has been serendipitously discovered by Cyprian Bergea, who's at the US Naval Observatory. He discovered this object in Pan-STARRS data, and this image here shows you an RGB composite image. I'm sorry, it's not looking so nice on the screen as it is on my laptop. So it's showing you an RGB composite image from the Pan-STARRS data using the infrared, red, and green filters. Pan-STARRS is a system of 2 telescopes operating in the optical and near-infrared regime. And what you can almost nicely see here is that Draci is a bright dipolar nebula. So you see a dark lane in the middle and 2 flared bright lobes next to this dark lane. And it's much bluer in comparison to its neighboring stars, indicating that there might be a hot star in its center. And also it appears to be a system observed at a high inclination. So most probably it's a disk that we observe basically edge on. And this is pretty much everything we can extract from the Pan-STARRS data, and this is why during the spring of last year we obtained SMA data from an DDT proposal, which ultimately helped us to prove that this must be a circumstellar disk through the observation of molecular gas in Keplerian rotation. And this also proves that this is most likely a very young disk with a few million years of age at most. And actually, I didn't want to talk about the name so much, but I'll do it. So Draculas Chivito, because Cyprian, who discovered this disk, he's from Transylvania, so he wanted to honor Dracula. And Chivito, because this disk resembles another very famous disk called Gomez's hamburger. And I cannot tell you why this was called hamburger, but I think it's pretty clear. You have a dark lane, and these two bright blobs basically look like the hamburger buns. And an analogy to this very famous disk, the discoverers decided to call it Draculas Chivito, and a chivito is a hamburger-like dish from Uruguay, and this is why they called it Draculas Chivito. Yeah, so as I said, I'll be calling it Draki throughout my talk. But what makes actually Draculas Chivito most exciting is not the name, but that it's huge. So it has a huge angular extent of almost 14 arcseconds in its bright disk emission. But unfortunately, it's barely, I don't think you can see it, but in the northern part of the disk, you see two faint flared filaments. We think that they trace the upper layers of the disk. And if you take them into account, the disk measures more than 20 arcseconds on the sky. And already this makes it most likely the largest disk on the sky in terms of angular size. However, in order to be able to convert angular extents into physical sizes, we obviously need to know the distance to this object. Unfortunately, I don't have any time to talk about the distance estimation today. I just wanted to briefly point out that we used these recently published 3D dust extinction maps by Gordian Edenhofer, and also Catherine collaborated with him. So Gordian was a visiting grad student last year in Alyssa Goodman's group, and we used their 3D dust extinction maps in combination with a catalog of young stellar objects that have precise Gaia distances in order to pin down the distance to Draki. At this point, we don't have an exact distance estimate, but the most likely one is around 370 parsecs, so it would correspond to the second peak here in the dust extinction map. And yeah, assuming now a source distance of 370 parsecs, we can then convert angular extents into physical sizes, as I said. So in the Pan-STARRS image, the disk has a radius of more than 1,000 AU, and in the SMA data, we have a disk radius of almost 2,000 AU. And these are radii, not diameters. And the reason why we combined the Pan-STARRS data with SMA data is pretty simple, because observing disks in different observational traces is extremely useful. So different wavelengths trace different parts of the disk and different materials, and therefore also different physical conditions. And you can see this really nicely here in this comparison of the famous TW Hydra disk, shown in infrared scattered light here on the left, millimeter thermal continuum in the middle, and spectral line emission here on the right. And what is most prominent is that TW Hydra has very different sizes in all of these different traces, but also shows different morphologies. And this is because these different types of emission arise from, as I said, from different parts of the disk. So the scattered light emission, as shown here on the left, arises from small micron-sized dust grains that are located in the upper disk atmosphere, and they basically reflect the light which is coming from the central star. And the thermal continuum arises from larger millimeter-sized pebbles that have already settled towards the midplane, to the cold midplane, and also drifted all the way to the central star, and this is why the millimeter continuum typically is much less extended than scattered light emission. And spectral line emission, as shown here on the right, traces molecular gas. It can arise from different parts of the disk depending on which molecule you're looking at, but in general it traces the gas component of the disk. And before I dive into the SMA observations, I want to make a little interlude here. So I'm sure everyone here has heard the sad news that Arno Penzias has died on Monday. And I'm sure most of you know him as Nobel Prize laureate, and that he won together with Robert Wilson the Nobel Prize for discovering the CMB, which is probably one of the most important findings in modern astrophysics. However, I wonder if, some of you know what other important discovery he has made. Sorry? Exactly. So he has, together also with Robert Wilson, and they were actually the first to observe carbon monoxide or CO in space. And this paper is actually pretty impressive. It's 2 pages long. Abstract is 1 sentence. But it's really concise. But it's they detected carbon monoxide in the form of a bright radio signal in the Orion Nebula. I can really recommend having a look at this paper. And this was, at least for millimeter and submillimeter astronomy, probably one of the most important findings, because this lay basically the foundation for our field. And so now I want to talk a bit about the SMA observations we've obtained. So the SMA, or submillimeter array, was in compact configuration, and we looked at 225 gigahertz, which corresponds to a wavelength of 1.3 millimeters. And this spectral range covered 12CO, 13CO, and C18O in its 2-to-1 transitions. These are the standard gas disk tracers that people usually first look at if they're interested in the gas component of disks. And these videos show you the basic data product of radio observation. So you have these so-called data cubes where you have an X and a Y position, and every pixel has an associated spectrum. And 12CO is the most abundant gas. However, C18O is the optically thinnest out of all of these 3. So most probably C18O gives us the most robust inferences on the total gas mass of the disk. And if we then collapse these data cubes along the spectral axis, we get these so-called integrated intensity or moment zero maps, shown here on the top. And they basically are a measure for the spatial distribution of gas in the disk. Very interestingly, the 13CO and C18O, which should be significantly less bright than the 12CO and also less extended, almost have the same spatial extent as the 12CO. We can also collapse this to get these so-called rotation maps or moment 1 maps that are basically direct evidence for Keplerian rotation. So they show that this disk, the gas in the disk must be in Keplerian rotation with 1/2 of the disk moving towards us, so the emission is being blue shifted, and the other half is moving away as the emission is being red shifted. And we can use these CO data then to extract important physical properties of the disk. I'll rush through it. I need 1 more minute. So we looked at the CO data to, for example, determine the mass of the star that is located in the disk. We can leverage the fact that this disk is in Keplerian rotation. So we use basically the Kepler's law, assuming some properties of the system, like the distance and the inclination. And by fitting then, so we define a slit along the disk's emission, and then compute these so-called position velocity or PV diagrams. If we fit then these Keplerian profiles, we can estimate the disk mass, the star mass, which we found to range between 2 to 4 solar masses. We can get an independent. We can also determine the disk masses from the dust, so the 1.3 millimeter dust. I will just rush through it. So using just standard assumptions of a gas-to-dust ratio of 100 and taking standard relations into account, we found a disk mass of 0.05 solar masses, which corresponds to roughly 54 Jupiter masses. Using the gas lines only, we can get an independent disk mass estimate, which we found to be at least 0.1 solar masses. And since the gas lines are all optically thick, most likely, this appears to be just a lower limit to the disk mass. So the real disk mass is most likely much higher, showing that in this few thousand AU disk, we have plenty of material present in order to form multiple giant planets. And we think that Draci might be a precursor of systems like HR 8799, which is also a young planetary system where we were able to directly observe at least 4 giant planets. These are inherently rare, so maybe, as I said, Draci might be a precursor of systems like that. And yep, I'll leave you with my conclusions. Thanks a lot, and I'm happy to take questions.
Thank you, Kristina, for mentioning this historic fact about Bob Wilson, and he actually told me, Bob Wilson, told me that when they proposed to detect CO and wanted to build the instrument, they were told it's a waste of your time, you should not do it, and you should not be funded to do it. And they had to resist all of that, and then when they built the instrument and looked at the sky, it was a signal that was factor of 1,000,000 above the noise. Factor of 1,000,000, and people argued before doing the experiment that it shouldn't be done. So that's a very important lesson. He said it was so a booming signal, and you know the amazing thing is that astronomers told them they shouldn't do it beforehand.
Yeah, impressive. Thank you.
Please go ahead.
Okay, to your remark, you know, the Astro 2010 decadal survey told that DHT should not be done. Anyway, so my question is, have you tried to look in 3D using optical spectroscopy, optical integral tube unit?
No. So this
Because we have an instrument now that is exactly the size of your source, and they can give you a sub-kilometer per second precision at MMT by inspect IQ.
We should definitely talk. So
Yeah.
even though this object has been discovered some years ago, we only started actively working on it last year, so it hasn't even publicly been announced. So we were already proposing the source for multiple other telescopes, etc. But we should definitely talk. We're trying to leverage our community and basically get as many data as we can get. Thank you.
Any other questions, comments? If not, thank you, Kristina.
Yep.
That was very
Thank you so much.
Hello? Great. I guess I better hold it. Wait, why my title was lost? Let me copy it from elsewhere. Somehow the title was lost. Here we go. All right. Thank you so much for having me here. I'm Minghao Yue, and I'm a postdoc nearby from MIT Kavli Institute. So today I'm very happy to get this chance to talk about our recent studies in the EIGER project about high-redshift quasars and their host galaxies. So I would like to thank you to the organizers to give me this chance, and also thanks for my amazing collaborators to make this study possible. So just in case that you are not familiar with the EIGER project, EIGER is a JRST GTO program using NIRCam to observe 6 quasars at high redshifts, namely redshift 6 and ish. So this includes NIRCam imaging in 3 bands and also grism spectroscopy in F356. So I would like to show you an example of the images we took in our project. This is one of the quasar fields, and the quasar sits at the center of this field. And in addition to this beautiful image, we also get, as I mentioned, grism spectroscopy of this field. So that means we have the spectrum of essentially everything in this image. So this excellent data set really allows us to do a wide range of exciting studies. You see, it covers lots of topics. And I mean, in this talk, I'm going to focus on quasar host galaxies that is reported in one of our recent papers. So just a brief introduction of the scientific background. It is pretty well known that supermassive black holes strongly co-evolve with their host galaxies. So here shows a very famous evidence that is the close correlation between the black hole masses and the host galaxy masses observed in the local universe. So such kind of tight correlation really tells us like there must be some very strong coevolution mechanism between black holes and their hosts. But exactly how does that happen? So this is the local relation. So the open question was like, how does this relation originate? Does this relation exist at redshift 6? Or does it exist at redshift 2? And if they do, what does it look like at those high redshifts? Indeed, characterizing the redshift evolution of the black hole mass versus host galaxy mass relation is one of the most important methods to understand how supermassive black holes and their host galaxies co-evolve. That's because the redshift evolution of those relations encodes the growth history of those monster black holes. So for example, this is a plot I grabbed from Voluntary 2012. So assume that black holes gain their mass prior to their host galaxies. At higher redshift, we will see that galaxies gather around the green line. Or if, like, we see things happen the other way, high redshift galaxies locate below the local relation and gathers around the blue line, we know that galaxies must have gained their mass prior to their black holes. So the point really is, by measuring the positions of high redshift galaxies on this plot, we can understand like what's happening through their growth history. And I mean, the discovery of high redshift quasars beyond redshift 6 tells us that there are monster black holes existing when the universe is less than 1 gigayears old. So ever since the discovery of those high redshift quasars, people have been trying to measure their host galaxy masses and put those guys on this black hole mass versus host galaxy mass plot. So one of the most important studies in this field is some ALMA observations trying to use the C+ emission line to estimate the dynamical mass of those host galaxies. And their finding is that those high redshift supermassive black holes lie above the local relation of black hole mass versus host galaxy mass. And if this is the case, this comparison suggests that high redshift supermassive black holes grow before their host galaxies does. However, there is a key caveat in this comparison. So if you pay close attention to this plot, I mean, for the high redshift quasars, we are using the dynamical mass from ALMA, but for the local relation, we are using their stellar mass. So we're not really comparing the same thing. And the reason why this is the case is because previously, the rest frame optical emission from those high redshift quasars are missing. And because of that, we don't really know the stellar mass of those high redshift quasars. And actually, we don't really know like whether, when we talk about the black hole mass versus host galaxy mass relation at redshift 6, what are we talking about? Does this relation even exist at that high redshift? We don't know. And we don't know like what do the quasar host galaxies at those high redshift look like. And all of the difficulty comes from the fact that quasars are so bright, and when we are trying to measure their host galaxies, I mean, for example, this is an HST image of a redshift 6-ish quasar. What we get is really a nice point source. So usually what we are doing is trying to distinguish the emission from the compact quasar and its extended host galaxy by the so-called PSF subtraction. I'm going to come back to this later. But previously, even with the superior power of HST, we still don't see anything after we subtract like the quasar component in this image. It is really after the launch of JWST when we started to be able to see the host galaxies of those very distant supermassive black holes. So in the first year of JWST's observation, we have seen great breakthrough in this field. I mean, despite that, people have spent like 20 years trying to see the host galaxies with HST and seeing nothing. But in the first year of JWST, we started to see some very exciting detections of the quasar host galaxies at high redshifts. This mainly contains like two aspects. The first is using NIRCam to see the stellar continuum, or like on the left side, you can see after subtracting the PSF, we see a nice host galaxy. And another way to do that is to use the powerful near-spec IFU, which is very useful in probing the diffused emission lines, say oxygen 3 and H beta of the quasar host galaxies. And in the rest of this talk, I'm going to jump back to our study. Again, we are using the deep imaging from the EIGER project as well as prism spectroscopy to understand the properties of those high-redshift quasar host galaxies. So as I mentioned, the key method here is to review the host galaxy emission using the so-called PSF subtraction, which makes use of the fact that the emission from the central AGN is so compact and is well described by PSF, and the emission from its host galaxy instead is kind of extended. So if you can somehow model the PSF component in the quasar image and subtract it from it, and you will see those extended emission. And the hard thing is quasars are so bright. I mean, usually the host galaxy is only like 1% flux of the bright quasar. So it really requires us to do careful PSF modeling and image fitting. So that's what we've done. We construct empirical PSF models, which we believe performs pretty well, and then do some image fitting, and we get the host galaxy masses, which we can use to build an SCD model to estimate their stellar masses. Okay, I think it's time for me to show you some very exciting detections. So there are 6 quasars in our sample. We have successfully detected the so-called nice, well-shaped host galaxy in 3 of them. So here are the images. So this is something we are trying to find in 20 years, and finally we see it. So we are very excited about that. And if you are wondering like what's going on for the rest 3, this is just a summary of those information. For the rest 3 that we don't report a host galaxy detection, actually we still, in 2 of them, see those extended emission features around after PSF subtraction. But you can see it's not like a nice elliptical shape, so it is hard for us to say like this is a well-defined host galaxy, but we still see something interesting which we interpret as maybe a possible merger or like a quasar-driven outflow, which we are still investigating. But I mean, the other one is so badly saturated, so we see nothing. But the point is like, there's a lot of variety and a wealth of features around those quasars and their host galaxies. So as I said, with the magnitudes of the quasar host galaxies, we can do SCD fitting to get their stellar mass. And remember, we also have prism spectroscopy of this field. That means we have the quasar spectrum, which can be used to estimate the black hole masses. And with this information, we can finally go back to this plot and to see where do our quasars locate on this relation. So if we put them on this plot, here is where they look, how they look like. And we also include other measurements from high-redshift AGNs and local galaxies on this plot. So I would say there are 2 key takeaways from this plot. First is, I mean, if we pay attention to all the colored points, these are all the high-redshift AGNs observed. I'll be quick. Observed by JWST. You can see there's definitely a positive trend. So that means this black hole mass versus host galaxy stellar mass relation already exists at redshift 6. And also those, despite the fact that those host galaxies, quasar host galaxies are pretty massive, there are still obvious overmassive black holes in terms of the comparison between those black holes and the local relation. They have black hole mass to stellar mass ratios that is 1 to 2 dex higher than the local relation. And just quickly show that we are trying to characterize some selection effects, and obviously selection effect cannot explain all of the difference. So yeah, I'm out of time, so I'm going to put my summary here. So the main exciting thing is that we see something that we are trying to see in the last 20 years, and we kind of confirm the overmassive black holes for we see in high-redshift quasars. And thank you for listening. I'm happy to take questions.
So in fact, your an offset corresponds to a factor of almost 100 or even more. constant in the black hole to star. Because usually it's 10 to the minus 3 relative to the bulge mass, and here you get only 1.
Yeah, that's right.
So that's a very significant fraction of the total reservoir.
I wonder, sorry, how much of that offset it may be due to an observational bias, because it happens in high redshift objects where you're not as sensitive to the low surface brightness component of the bulge, which could carry a lot of mass. Have people looked into that?
So people have been discussing some observational bias. So in our case, I think first of all, like the stellar component, you can see actually. Oh, I should mention those images are 3 times 3. So actually, those 3 detections all have like pretty large host galaxies in terms of like expected radius. They are all like 0.3-ish arc second. So I'm not really worried about like not resolving some component or like, I mean the images are pretty deep. I believe those kind of systematics will only contribute to maybe like 10%-ish level. It won't like change the estimated host galaxy mass by a factor of something. Another selection effect people have been talking about is the so-called Lauer's bias. That means essentially since those quasars are selected to be very luminous quasars, I mean more luminous means they are likely to have more massive black holes, right? Assuming like kind of a fiducial distribution of the Eddington ratio. So that, I mean, this plot I'm trying to mimic this effect. The underlying, the solid lines are kind of the distribution of local agents, and I'm using this relation and assume there is no redshift evolution, and what will we get after taking into account like the flux selection induced bias, and that is the color contour. We can see those kind of bias will contribute to the so-called overmassive black holes we see. However, our quasars still have like even larger black hole to host galaxy mass ratios. Although I would say this is very preliminary because this kind of studies could be very complicated.
But you can actually verify it with dynamics, right? Because the black hole would dominate the dynamics in the inner part of the galaxy. So if you had some spectrum, you could tell the narrow line.
Yes, exactly. So what we are doing, I mean, we have asked for near spec IFU to get some narrow line kinematics spatially resolved, and we are also trying to use ALMA to probe like the kinematics around the black hole. So using C+ line or CO line.
Go ahead.
Don't you think that if the bulge is compact, you can actually subtract it together with your quasar emission?
So you mean like some of the PSI
sitting in the bulge that you'll basically remove some of the stellar mass, thinking that it's in fact the AGM continuum because you're at lower resolution. I mean, like the images, they don't have spectral resolution.
It is possible, I would say, but I mean, personally, I don't think this will contribute a lot to the systematic errors because, first of all, those galaxies are pretty massive. They are 10 to the 10 stellar mass. I mean, just assuming like a normal mass to radius relation, we will expect that the bulge component should be, kind of resolved, right? I mean, JWST has a PSF size of 0.1 arc second, so it should be able to resolve such massive galaxies. And also, there's another systematic error that is in the SD fitting, which is usually like 0.3 to 0.5 dex at least. So I think that is actually the dominating term compared to like how much flux is lost in this image fitting. But sure, I mean, we definitely want a better PSF model to, describe this, to do the image fitting as accurate as possible. I think that your point is very important when we come back to the fainter AGNs with smaller host galaxies, and their host galaxies are supposed to be more compact. For example, there are some discussions about the so-called little red dots recently found in JWST, which are the blue points here. And if we are talking about these agents, we will expect that their host gas is compact, and the systematic you mentioned will be a big issue, I think. But for the quasars, since their host gases are so massive, I don't really worry about that. And how we should improve the image fitting for the faint ones, we're still working on that, but I agree that will be a very important point.
Last question, someone, do you want?
Similar question.
Oh, similar. Okay, we are.
Okay, thank you.
Thank you so much.
So does it work? Hello?
Your answer is all.
Thank you.
So, thank you for being here, and I really appreciate this opportunity. I'm Wang from another Cavity Institute at Peking University, and today I'm going to be talking about how to connect galaxies across cosmic time. So first, I want to pose this problem, and then I want to provide some partial solution to this problem. So I'm going to start with the general big picture question: how do galaxies evolve? Someone here want to approach this question through numerical simulations by producing realistic galaxies just as we see in our real universe, while others want to approach this problem by posing some toy models to capture some essential processes in galaxy evolution. And today I'm going to be talking about another method to establish the empirical connection between galaxies at low redshift and at high redshift. And then we can study the evolution of these galaxy properties. So allow me to lay out this problem in more details. So this is a typical galaxy redshift survey with galaxies at different redshift. And we know that galaxies at a different redshift are causally irrelevant because they are galaxies at different locations. But thanks to the limit of light speed, high-Z galaxies are not only distant in space, but also distant in time. So in principle, we can establish an empirical connection of galaxies at different redshift so that we can study the evolution of their properties. However, we can put it in a mathematical framework. What we can get from galaxy observation is a set of time-dependent distribution functions from which we want to derive the phase space equation of motion of these galaxies. For example, how a low-mass small galaxy at high Z got evolved into the large and more massive galaxy at redshift 0, and how a star-forming galaxy at redshift 2 got quenched when they evolved to redshift like 1. So those evolutionary trajectory is something we are pursuing. And one must realize that there are infinite number of equations for motions that can give you identical time-dependent distribution functions that you directly observe in observation. So to break this degeneracy, we must incorporate some prior knowledge or make some assumptions. And many efforts has been done toward this direction. For example, people are using so-called the constant cumulative lump density method, which basically assumes that at the fixed moving volume, the most massive galaxy at high Z will evolve into the most massive galaxy at low Z. So for the second massive and third massive. So this sounds reasonable. But we should know that galaxies will merge with each other. So when two massive galaxies merge with each other, the rank of all the low mass galaxies will be messed up. So this method is not applicable. And to solve this problem, people are proposing this evolving cumulative lump density method, which basically use the merge of subhalos extracted from the embodied simulations to calibrate the merge of galaxies in observation. And we did refine the method, but still this method cannot resolve another problem. So we know that galaxies at redshift 0 could be either star-forming or quiescent. And we expect that the progenitor stellar mass of the quiescent galaxy should be more massive than that of the star-forming galaxies, because quiescent galaxies stopped making new stars a while ago. So their progenitor must be more massive in order to achieve the similar stellar mass at redshift 0. So this method cannot reproduce this phenomenon. So to solve this problem and to guide the future development, we propose a general framework. So our strategy is that shown in this figure, left hand, the causally irrelevant galaxies at different redshifts, and on the right hand, we have the subhalo merger trees extracted from embodied simulations. So these dark matter halos are causally linked with each other in the simulation. So what we are going to do is to use the so-called the galaxy halo connection to populate the observed galaxies into the simulated dark matter halos, so that we can connect galaxies across cosmic time and study the evolution of their properties. So as a preliminary test, we use these two widely used methods to establish the connection between galaxies and dark matter halos. And the first one is so-called the subhalo balance matching method, which assumes that the more massive galaxy lives in more massive halo, reasonable. And the second one is called the age distribution matching method, which assumes that the quiescent galaxy lives in old halo, also reasonable. And then we can connect the galaxies and study the evolution of their stellar mass. So this is a test on the illustrious TNG 100 simulation. So we select the galaxies at redshift 0 and beam these galaxies according to their descendant halo mass in different columns and the different stellar mass in different vertically shifted curves. And then we also separate the galaxies according to their star formation activity at redshift 0, so either be quiescent or star forming. And the true answer in TNG 100 is plotted using these arrow bars. And the shaded region is the prediction of our method. So they match with each other reasonably well. So the next thing is to apply it to observation. So we use observational data to apply the just introduced procedure, and we got this result. So here I'm plotting the look-back time when the main progenitor galaxy has accumulated like the 10% and the 50% of their stellar mass at redshift 0. So I plot this characteristic time as a function of the descendant stellar mass, and different curves are for different descendant halo mass, and the left and the right are for the star forming and the quiescent descendant galaxy. So this is the quantitative result, and the qualitative take-away message is that galaxies in quiescence or with high stellar mass or in more massive halos are formed earlier. Okay, so this is just one method to connect the galaxies. And here I briefly introduce another method to do the similar thing. So we need to first connect the structures across cosmic time, and then we can study the galaxy evolution embedded for these galaxies embedded in these structures. So here I'm showing you the assembly of a dark matter halo extracted from the embodied simulation. So from the redshift 0 descendant cluster or a dark matter halo, we can trace its formation history in the simulation, and we can find a collection of galaxies or dark matter halos at high redshift, which will eventually collapse into this calm halo. So this is called a protocluster. And what we are going to do next is to first identify these structures in observation, so-called the protocluster finding. And what we're going to do a similar thing at redshift 0, so-called the cluster finding. And the most exciting thing is that we are going to establish so-called the cluster-protocluster connection in simulation. And the best thing is that cluster and protoclusters are large objects in our universe. Their size could be several megaparsec or even larger. So on these larger scales, we don't need to consider any baryonic physics. We just need to consider the gravity. So we can safely study this cluster-protocluster connection in simulation and apply them to observation to connect the structures across cosmic time and study the galaxy evolution embedded in these structures. This is still an ongoing work, but I can show you some interesting results we found about the secondary galaxy cluster-protocluster connection. So here I'm showing you two protoclusters extracted from the embodied simulations at redshift 2. And in simulations, we can trace their evolution to redshift 0. And we found that these two structures will evolve into dark matter halos with very similar descendant halo mass, but they look very different at redshift 2. So there is a large diversity to capture. And so we proposed a so-called the secondary cluster-protocluster connection. So in the first two panels, I'm showing you the relation between so-called the protocluster size, defined using this formula, versus the central to total stellar mass ratio at redshift 0, which is observable. And we can see that these two properties are strongly correlated to each other. So we can use this correlation to establish the secondary connection between clusters and protoclusters. So the take-home message is that we propose two different methods to connect galaxies across cosmic time. The first one is to use so-called the galaxy halo connections to populate the observed galaxies into the simulated dark matter halos, and then we use the subhalo merger tree to connect galaxies across cosmic time. And the second method is to connect structures across cosmic time. Then we can safely study the evolution of galaxies embedded in this structure. And my last word is that it takes us decades to unify the picture of galaxies at different wavelengths. And we finally enter a multi-wavelength era. And I think in the upcoming decade, we are entering or we are stepping into a new era that we can see or view the evolution of galaxies from an evolutionary perspective by combining galaxy surveys at different redshifts. So this is what I'm going to talk. Thank you.
Any comments or questions? We're a little bit over time, so some people need to go. But thank you so much for the presentation, and thank you everyone else, and we'll see you all in a week.